In today's video, we're going to start a series of videos on the amount of substance topic, often referred to as the moles topic, and it incorporates lots of different skills that you've both come across at GCSE and will be expanded upon in A-level. Now, before we get that started, I want to give a final call to this idea of formula literacy. The number one thing that students struggle with is formula literacy. If we don't get this right, then we really find it hard to build a consistent understanding of what's going on in each chemical reaction. So I'm leaving this page up here, and I'll put a link right now to the formula literacy video. Make sure you're regularly practicing your formula literacy, and have a go at this video if you're finding it difficult. Okay, let's crack on. So we're going to start off first of all by talking about the concept of the mole, the concept of masses, and the relative molecular mass. Now you need to be able to define the relative atomic mass, and when you give that definition, you need to define it as the mean mass of one atom over 1/12 the mass of carbon-12. Now you can also be asked to define something called the relative molecular mass, and the relative molecular mass is the mean mass of one molecule over the mass of 1/12 of carbon-12. Now, you may also think of the relative molecular mass as the sum of the relative atomic masses of the elements in a compound. So it wouldn't be particularly unusual for you to think of the relative molecular mass of H2O as 1 plus 1 plus 16 and 18 grams per mole. That's fine. But if you're asked to define the relative atomic mass or the relative molecular mass, then please use this definition: the mean or average mass of one of the things divided by 1/12 the mass of carbon-12. And why did we use carbon-12? Well, because it was easy to get a high level of purity, and it gives us a nice standard to compare everything to. Sometimes you'll see a thing called the relative formula mass. Now, the difference between the relative formula mass and the relative molecular mass is not much really. Essentially, when we think of using the term relative formula mass, we're normally thinking it's an ionic compound. So for example, we'd ask for the relative formula mass of sodium fluoride, but the relative molecular mass of water. And this is because ionic compounds don't form molecules, so we can't use the word molecular mass. But the definition can be exactly the same, essentially. And these two words are often used interchangeably. So this is our key definition. How are we going to learn this? We're probably going to put it on a flashcard. On one side, we're going to have what's the relative atomic mass, and on the other side, we're going to have the mean mass of one atom to 1/12 of carbon-12 atom. And we're going to practice that regularly to make sure it's completely ingrained and we don't possibly ever make a mistake. It's as simple as that. Now, there is a concept that we talk about sometimes called the water of crystallization. And to explain that, I'm going to take you back to a part of your GCSE. We're going to look at something we learned about in the reversible reactions. We learned about a compound called copper sulfate. And for the record, copper sulfate has the formula CuSO4. Now, we learned about two forms of copper sulfate. There's a classic copper sulfate, which is kind of blue crystals, and you may have put them in a dish and you may have heated them, and they may have turned into white crystals. So we've got the blue version and the white version, and we add heat to that situation and it goes from blue to white. We call this version the hydrated salt. And what we mean by that is there are water molecules trapped inside this version of copper sulfate. For now, just think of it like there are gaps in the crystal lattice, and in those gaps, water molecules can fit. And different elements have different size gaps when they form ionic compounds, so different amounts of water molecules can fit in the hydrated salt. We call the white one the anhydrous, which means it is not got water in it. And when we add the water to it, it releases heat in an exothermic reaction. So that's where we covered this. We covered this on this idea of that we can put heat in an endothermic process and turn it to the white version. Then we can wait for that to cool down, and we can add the water and turn it back to the hydrated version, and we release heat energy as that does it in an exothermic reaction. Now, the reason I'm talking to this about now is because we need to know how to work out the relative formula masses of hydrated salts, and it's actually incredibly simple. So how do we work out the MR of this hydrated copper sulfate then? Well, quite simply, we're going to make sure that this dot becomes a plus. So for the copper sulfate part, we've got 63.5 plus 32.1 plus 4 lots of 16. And that's going to give me 159.6. And for the water, I've got 5 lots of water. Now water is 1 plus 1 plus 16, or 18. We can just learn sooner or later it's 18, and that gives us a value of 90, and I'll put a 0 in so I keep my decimal places in both of them, and I'm just going to add them together. When I add them together, I get 249.6 grams per mole. So it's not particularly complicated, it's just an extra step that we need to be aware of. So here's one for you to have a go at. Okay, pause the video, use your periodic table. Can you work out the relative formula mass of hydrated sodium sulfate? Off you go. Okay, how did you go? Here's the answer here. You should be getting 322.1 grams per mole for this version. Notice there's a lot more water in here, and for the record, I just jumped straight to 18. Over time, you get used to certain relative molecular masses off the top of your head. One final practice then, please. Okay, pause the video, and work out the hydrated magnesium chloride, please. So here we have the workings for the magnesium chloride one, 95.3 and 108, 203.3 grams per mole for the magnesium chloride. That's it. I'm sure you've got both of them right. It's not that tricky to do, but it's important that we understand it. Now, this will come up a bit later on because we can also be given problems to try and find this value. So sometimes they can give us something like MgCl2 dot, say, XH2O, and they can give us all the other numbers, and we need to find out this mystery water of crystallization. So look out for that in a later video. Okay, so now we're going to push on and talk about the mole. Now, the mole is something that people get a real tiz over, to be honest with you, and it doesn't have to be that way. I think it's one of those things that people end up with a partially sound understanding of, and so it becomes quite intimidating that there is this idea of this kind of secret chemistry that they haven't maybe paid attention to or been taught about by their teacher that makes everything foreign to them. So I just want to say before we get into this topic in any more detail that there will be no secret chemistry. Your teachers will make sure that you are aware of the kind of things that can happen in chemical reactions. There won't be magical materials all of a sudden that crop out of nowhere that you have no idea of, or that don't obey the underlying principles that you've been taught. Okay, so if we're talking about basic rules that are being implemented, you know, if something has wings and quacks, let's assume it's a duck. Let's not assume it's a duck-billed platypus. Now in this picture here, I got some donuts, and the reason I got donuts is because 1, I love donuts, and 2, there are 12 of them. And we know that in the English language, if we want 12 of something, then we also want a dozen of them. Okay, and we know that this word dozen means 12. So if I want 2 dozen donuts, in my head, I know that is 2 times 12. Oh, let's write neatly. And so I know I'm going to end up with 24 donuts. All I'm doing is just substituting a word for a number. And in some ways, the mole is the same thing. The mole uses a number called Avogadro's number, or Avogadro's constant. And you'll sometimes see it as a capital L, or you might see it as a capital N with a capital A in subscript. And what that's basically saying is, just like dozen uses the number 12, Avogadro's constant equals 6.022 times 10 to the power of 23 things. So we could have a mole of donuts. It would be a huge amount of donuts, way too many donuts even, some would say, but we could do that quite easily. Now the thing that's really key for us is what this means, because on the periodic table we have relative atomic masses, e.g. we know, let's pick a good example, carbon has a relative atomic mass of 12. What Avogadro's number lets us do is it has this relative atomic mass in atomic mass units, and by timesing by Avogadro's number we turn that into a mass in grams. So carbon becomes 12 grams of carbon 12, and we call this unit, this amount where the relative atomic mass is the mass in grams, a mole of a substance. So if I have 1 mole of carbon 12, I've got 12 grams of carbon 12. If I have 1 mole of carbon 13, then I need to have 13 grams of carbon 13 to have a mole of it, because it is heavier. So each one takes up a greater mass. It's important to realize that moles are units of things. So some moles contain more stuff than other moles, and moles are never conserved in a reaction. I'll say this a few times. For example, if I was to have H2 as a molecule, the relative molecular mass of H2 is 2 grams per mole. Therefore, if I have 2 grams of H2, I have 1 mole. But I don't have 6 times 10 to the power of 23 atoms. I have 6.022 times 10 to the power of 23 H2 molecules, but each molecule is made of 2 hydrogen atoms, so I would actually have 1.2 times 10 to the 24 hydrogen atoms. I don't need to worry about what my substance is made of when I'm talking about moles. If I have a mole of H2, I've got a mole of H2. If I have a mole of glucose, C6H12O6, then I've got 1 mole of glucose. It's made of 6 moles of carbon, 12 moles of hydrogen, and 6 moles of oxygen. But I don't need to worry about those numbers. These subscript numbers are not useful when I'm thinking about the number of moles, because these are all in 1 molecule. So that's my little tip for you to think about. Remember, when you're working out moles, they don't have to be conserved. You can have 15 moles turning into 2 moles. That's completely fine. But you do have to know, if you want to know atoms, you have to know what each thing is made of. So moles are essentially calculated by getting the mass in grams and dividing it by the MR in grams per mole. So if I have 15 grams of carbon 12, then the moles I'm going to have is equal to 15 divided by 12. Okay, and 15 divided by 12 is a pretty easy one to do in your head, but don't be afraid to get your calculator out if you want to. It's going to give us 1.25 moles of carbon. What about if I had 15 grams of hydrogen? How many moles would I have then? Well, my moles are going to be equal to my 15 grams divided by the relative molecular mass of hydrogen, which in this case is 2. I'm going to have 7.5 moles of H2. So the same mass, because the molecules are very different sizes, and if I was to do it with another molecule, I'd have less than 1 mole. So if it was a big one, let's say I was doing it with chlorine, which is 71, then I could go, my mass of chlorine is 15 grams, and I could divide it by my 71, so I could have 15 grams of Cl2 and it would be 15 divided by 71, and that's going to give us 0.21 essentially moles. So it doesn't matter what mass we've got. Most people don't remember it in that format. Most people choose to remember it in this format. Mass equals Mr. Moles. Okay, our mass is equal to the relative molecular mass times the number of moles. So we're after this, and then we can just rearrange from here if we need to. This is the way it is often most memorable. So if you want to know what mass 2.0 moles of lithium would be, then we're just going to go 2.0 times 6.9, and that will give us our answer, 13.8 grams. It's as simple as that. Let's tidy up that 6. I can have less than 1 mole, and I can have multiple things. So what about 0.1 moles of CO2? So I can go 0.1 times 44, which is the relative molecular mass of CO2. That would give me 4.4 grams. It's pretty straightforward. The final thing they can ask you to do is they can ask you to work out the mass of a single atom. This is much rarer, but it often can occur, and we're going to use Avogadro's number here. So if we know that 1 mole of carbon 12 is 12 grams, then we can work out what the mass of 1 atom would be. So we can go the mass of 1 atom equals 12 grams divided by Avogadro's number, 6.022 times 10 to the power of 23. And then when we put that in our calculator, we get 1.99 times 10 to the minus 23 grams. And that's how we work out the mass of 1 atom. So if we looked at the mole equation, and what I want to do is use the mole equation to answer these questions. Pause the video, okay, and make sure you know exactly which elements you're after. I do want to point out that the 2, I want to remind you of your formula literacy, will mean this will be a Cu2 plus ion, okay, copper 2. Make sure you account this as well, kilograms of mercury, don't make the mistake there. When you're finished, unpause and I'll show you the answers. Good luck, off you go. So here's our answers. How did you get on? Pause the video and mark them again. Make sure you are checking them off. If you're not sure why one is, go back and rewatch part of the video at the chapters and make sure you get it right. Well done. Now in this activity we're going to use masses Mr. Mole, masses MR times moles to work out the mass of each of these. Pause the video. Make sure you take a careful if it says molecules or if it says atoms. Some molecules are diatomic, remember, which means they need 2 atoms in the molecule. When you're finished, unpause and we'll go through the answers. So here's our answers. Bearing in mind that the first one you could have given in grams or kilograms, could be 2.070 kilograms. How'd you get on? Hopefully you remembered in J to include the moles of water. Now we know about Avogadro's number, we can use that in some calculations. Read the questions carefully, make sure you know if they're going to be molecules or atoms and which bit you're trying to work out. You'll need to use the mole equation as well in places to work out things you need to get to the answer. If you're ever unsure, get to moles and then you can work out from there. So here's our answers. How did you get on? Make sure you used your standard form correctly. Excellent, well done. So our final thing is to kind of show you the difference between A-level and GCSE. At GCSE we've been doing some of these calculations, but they've been quite straightforward in their scenarios. Now what I've got for you here are some more challenging examples that are in a context. They involve conversions of masses maybe, or a few extra steps to get to the part where you need to. So read them all carefully, have a go at each question, pause the video, then when you're ready for the answers, unpause and we'll show you these final answers. Good luck. So here's the answers. Okay, make sure you check them carefully. I've given my answer to question 1 in pence. You may have rounded up to pounds, I suppose. So double check that. How did you get on? Excellent. This brings us to the end of this first part of the amount of substance topic. We've looked at what the mole is, how it works, why it's useful, and how to convert from one thing to another. Okay, if you found anything difficult with formula literacy, make sure you go back and check that video again. Thanks for watching, and I'll see you next time. Bye-bye.